Now let us see this question. So, on a planet whose size is the same and mass 4 times that of Earth, find the amount of work done to lift 3 kg mass vertically upwards through 3 meter distance on the planet. The value of g on Earth's surface is 10 meters per second. So, if I calculate the amount of work done on the surface of the Earth, then the work which I will do, it will be converted into gravitational potential energy of that body. So therefore, potential energy of a body can be written as mgh if the height lifted is very small. So mass of the body is 3, g value is 10 and height raised is 3 meters. So therefore, total it is 9 tens are 90 joules will be the work done. Similarly, now I am trying to calculate this work done on a planet whose size is the same, but mass is 4 times that of Earth. So we know that work done depends on g value. So first of all, we will write equation for g here. So g is equals to gm divided by r square. So if this is the equation for Earth, then it is 10 meters per second square. And if I write g value for the planet, then it is g into, so mass is 4 times, so 4 into me divided by, and he gave that size is same, so I will write r square itself. So this is nothing but 4 into ge, so 4 into ge value is 10. So 40 meter per second square. So this is the acceleration due to gravity present on the planet. So now, if I calculate the work done again, then it is m into g planet into h. So therefore work done is equals to mass is 3, g value is 40, height is 3. So work done is equals to, so 9 3s are 36, so 360 joules will be the work done. Friends, now let us see this question. Find the altitude above the surface of Earth at which acceleration due to gravity reduces by 36% of its value on surface of Earth. So here if I see the percentage of reduction, it is 36%. So it is much greater than the actual value. So already in our theory part we have discussed the equation for percentage reduction in acceleration due to gravity. So percentage change is equals to 2h divided by r into 100. But this equation I cannot use in this condition because this is the percentage change only when height from the surface of Earth is very small or change in g value is very, very small. But here this is a considerable change in g value, so definitely I have to go for the general equation of solving this problem. So that is, so we have g is equals to gm divided by r square and g dash is equals to gm divided by r plus h whole square. So this is g value on the surface of the Earth. This is the g value at a particular height. So if I divide both of them, I will get g dash by g is equals to r square divided by r plus h whole square. So therefore g dash is equals to g r square divided by r plus h whole square. So therefore g dash is how much? So 36% has reduced, it means 64% is remaining. So 64 divided by 100 is 0.64. So therefore 0.64 g is equals to gr square divided by r plus h whole square. So g and g get cancelled. So now these are the remaining terms. So if I square root them on both the sides, then I will get 0.8 is equals to r divided by r plus h whole square. So so here there is no square. So 0.8 into r plus h is equal to r. So therefore 0.8 r is plus 0.8 h is equal to r. So if I this 0.8 if I take to the other side, then 0.8 h is equals to r. If I take common, then it is 1 minus 0.8. So nothing but h is equals to 0.2 r divided by 0.8. So it is nothing but 2 into r divided by 8. so which is r by 4. So therefore h is equals to r value is 6400 kilometer divided by 4. So this is 4 ones are and 2 is remaining, so 4 6 are, so therefore 1600 kilometer will be our answer. So therefore at a height of 1600 kilometer, r value reduces by 36% of its actual value. So what would be the time period of rotation of Earth? So that bodies at the equator would weigh 40% of their actual weight. So weight is decided by the gravitational force, or weight is decided by the acceleration due to gravity. And due to rotation of Earth, already we have derived an equation for acceleration due to gravity due to rotation of Earth, which is equals to, so g dash is equals to g into g minus r omega square cos square lambda. So this equation already we have derived now. So weight has become 40%. So therefore g value also should become 40%. Then only weight should become 40%. So therefore g dash 40 by 100 into g dash is 0.4 into g is equals to g minus r omega square into cos square lambda. So lambda is nothing but a latitude of a place, which we have already discussed. So for example, this is the Earth and this is the equator. For example, this is a point. Then this angle we call it as lambda, which is called the latitude of the place. Now he is asking the position at the equator. So at the equator, lambda value is 0. Cos lambda is cos 0 is 1. So cos square lambda is also 1. So therefore 0.4 g is equals to g minus r into omega square. So therefore I can write it as 0.6 g is equals to r into omega square. So therefore omega square is equals to 0.6 g divided by r. So omega is equals to square root of 0.6 g divided by r. But here he is asking to find out time period. So therefore we know that time period is equals to 2 pi divided by omega. So therefore omega, so therefore t is equals to 2 pi divided by omega value is square root of 0.6 g divided by r. So t is equals to 2 pi into square root of r by 0.6 into g. So therefore t is equals to 2 pi into square root of 6400 kilometer into 10 power 3. If I multiply, then it converts into meters. 0 pi divided by 0.6 into g value I will take approximately to be 10. So if I do this calculation, then I will get the time period to be 6489.24 seconds. So this will be the time taken if weight reduces by 40%. A body stretches a spring because of its weight by a particular length at the equator. At what height the body stretches the spring by same amount above the south pole? That is the question. So for example, if you consider this as the Earth's surface, then he is asking about 2 points. So if I consider this to be my equator and this to be my south pole, so initially here there is a spring like this, and here there is a mass, and this mass is stretching this spring by certain x value on the surface of the Earth. So if this spring, if this mass should extend this spring or elongate this spring by same value on the south pole. So for example, above this south pole, the same mass elongates the same spring by the same distance of x. So again elongation should be x in the same condition. Then what is the height at which I have to place this spring and body system? That is the question. Now the question is, why this change is happening? So why here on the equator, on the surface of the Earth, on the equator, it has a different elongation, and why the spring has say different elongation on the south pole at a particular height? Already we have studied that g value depends on many factors. So one of such factors is it depends upon shape of Earth, and g value also depends upon what you call rotation of earth also. So here the change of g value due to shape of earth is very small in this condition. So this condition I am neglecting, and I am calculating g value change only because of rotation of earth. So at the equator, the g value because of rotation of earth can be written as g dash is equals to g minus r omega square cos square lambda, where lambda value is 0, where lambda is the latitude of the place. And already we have discussed that latitude is 0 degrees at the equator. So therefore g dash at equator is equals to g minus r omega square cos square lambda will become 1. So g dash is equals to g minus r omega square. Similarly, if this is at equator, similarly if I calculate the g value at the poles, then also it is g minus r omega square cos square. But here at the equator, at the poles, the latitude of the place is 90 degrees. So cos lambda is cos 90, which is equal to 0. So g dash at poles is equal to g itself. So because of rotation of earth, g value at the poles will not change. But so therefore g value reduces at the equator by this much factor. So therefore definitely the weight of the body will be lesser at the equator and weight of the body will be greater at the poles because of this factor r omega square. So therefore if I place this spring and body system at the equator and at the poles at the same height, then the elongation produced on the south pole will be greater, because here g value is greater when compared to the equator. So then how can I produce the same elongation in both of them? One thing which I can do is I can take this spring mass system above the surface of earth, or this spring mass system I can take below the surface of earth also. So we know that g value is maximum only on the surface of the earth. So if I take this spring mass system above the surface or below the surface, g value reduces. But he is asking height only, that is altitude from the surface of the earth. So therefore, and because of rotation, g value reduces by a small factor. So therefore I have to take this spring and mass system only by a small height above the surface of the earth. So therefore for small heights or for small changes in g value, I can always write g dash is equals to g into 1 minus 2h divided by r. So this is the g value because of altitude of the place, that is height from the surface of the earth. So this g value on the south pole and this g value at the equator, if they are equal, then the elongation produced in the spring will be also equal, because weight of the body will become equal if g values are equal. So therefore by equating 1 and 2 I will write, so g minus r omega square is equals to g into 1 minus 2h divided by r. So g minus r, omega value is 2 pi by t. So 2 pi by t is 24 hours, that is time taken for rotation of earth. But it is in hours, we convert into seconds, that is 3600 seconds whole square is equals to g into 1 minus 2h divided by r. Okay. So therefore again if I do some more calculation on this one, g minus r value can be written as 6400 into 10 power 3 meters into 2 pi divided by 24 into 3600 whole square is equals to g into 1 minus 2h divided by 6400 into 10 power 3 meter. So if I do this all calculation, so finally I will get h value, which is equals to 10819 meter, or you can approximately write it as 10 power 8 kilometer. So this is our answer. So it means that this is the 10.8 kilometer. So this is the height at which I have to take this spring and mass system above the surface of the pole, so that G value will become equal at this at a particular height of the pole, and same value exists at the surface of the earth near the equator also. Listen. If radius of earth were to shrink by 1% of its mass, 1%, if its mass remains the same, then find percentage change in acceleration due to gravity on the earth's surface. So these type of problems very easily we can do by applying the concept of logarithms. So let us see how we can do. So we know G is equals to Gm divided by R square. Now applying logarithms on both sides, I can write a log G is equals to log Gm minus 2 log R. So G and M both are constant, so both of them I am writing in one logarithm. Now if I differentiate this one, then differentiation of log x is 1 by x, so therefore 1 by G, but G I have not differentiated, so I will write a dg, and this is totally a constant, so differentiation of a constant will become 0, so minus 2 into log r can be written as differentiation of log r is 1 by r, and r I have not differentiated, so again I will write dr. So dg by g is equals to minus 2 into dr divided by r. Now if you multiply both sides by 100, then dg by g into 100 is equals to minus 2 into dr by r into 100. So dg is very small change, this is the total value, so this is the fractional change. Fractional change multiplied by 100 will give percentage change. So therefore percentage change in G value is equals to minus 2 times of percentage change in R value. So it is already given that percentage change in R value is 1. So therefore dg by G into 100 is equals to minus 2%. So minus 2 indicates that G value is reduced. So therefore percentage change in acceleration due to gravity is minus 2%. That is G value reduces by minus 2%.